In this video, we'll look at compound angles. And before we get started, just a quick reminder on how to do mathematics. So number and copy the examples. Ask your teacher or your tutor if there are any steps that you do not understand. Number the questions, and unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answers. And then mark your work, and if you get something wrong, write down the corrections. Make sure you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. Now to start off, these are the identities for the compound angles. And it's good if you know these off by heart. They are in the examination for Matrics End Year examination. They are in your formula sheet. But if you do know them off by heart, they are much easier to recognize if they pop up in a sum. So the way I remember them is if I have sine A plus B. Now sine is the good guy and cos is the bad guy. So sine A plus B gets expanded. Then you have sine A cos B plus cos A sine B. So what sine does is he, because he's good, he shares. So first he takes a bit for himself and then he gives to cos. And then his sine changes, stays the same. And then cos goes first and then sine goes. And then it's identical with the negative, except the sign stays the same. So your negative will have a negative in between the two terms. Now if we go over to cos is the bad guy. So cos starts off and he just takes everything for himself. So he's just cos A, cos B, and then he's a rebellion. So he kind of just wants to change things. So he takes that plus and he makes it a minus, and then whatever is left over he gives to sine. Now if it is a minus, it's basically the same story, except he changes the minus now into a plus. So that's just one way that I use to remember these identities. Now for an overview of this video, we will first look at expanding, then simplifying, then using or evaluating and our special angle rules, then quadrants where we use the cast diagram, then look at identities and equations. All of these that we've done previously, except now with compound angles. So we start with expanding. So if you know your formulas, these are a piece of cake, because I basically now have sine 2 alpha plus 40. So in terms of A, or instead of A and B, I just now have 2 alpha and 40. So expanding, remember sine starts off with sine 2 alpha and then gives to cos 40. The sine stays the same, which makes that then a plus, and then cos gets a turn to go first, 2 alpha and then cos 40. And that's sine 40. Alright, so that's just expanded using the identity. Question 15.1. So we need to expand cos A minus 2B. So since this is cos, he takes everything for himself. So cos A, cos 2B, and then he changes the sign to be plus, and what's left over, sine gets to sine A, sine 2B. Okay, so that was real easy. That's just how we expand those identities. Next, we'll look at how to simplify. So in this case, I am given cos 2 theta, cos theta, minus sine 2 theta, sine theta. Now, this is where knowing the identities off by heart comes in quite handy. So I can see immediately we have cos. So, okay, I know this has to be cos. And then, obviously, this 2 theta and theta are my two angles. So I have cos, and then it's 2 theta. This cos changes the sign, so this must be plus theta. All right, and then I can go a bit further, and I can say 2 theta plus theta is then cos 3 theta. Question 16.1. So you have sine 5x times our cos 2x plus cos 5x sine 2x. Now, sine, then cos. So this belongs to sine. And here cos, then sine. So we know now this is sine. And then my first angle, which is 5x. And then sine stays the same. Plus 2x. And then just simplifying that fully, we get sine 7x. Example 17, we have to simplify the following. Now, here we have sine 3 beta, sine 2 beta, cos 3 beta, cos 2 beta. Now, this one isn't identical to anyone we know, although we can swap the two terms around. We can say this is cos 3 beta, cos 2 beta, plus sine 3 beta times by sine 2 beta. Now, in this case, we could have just written down now the final answer. We know this is cos's identity, cos 3 beta minus, because it changes sine 2 beta. You would think, why go through all the trouble by rewriting this whole thing where we can clearly see it is cos. If you have a negative here, then it would complicate matters. So always try and get it in the right shape and then simplify it. So this is then just 3 beta minus 2 beta. So this is just cos beta. So for question 17.1, so once again, I've got a sine and a sine and a cos and a cos. So this belongs to cos, although cos is first. So by swapping these two terms, remember the sign in front of the term goes with the term, meaning we have to say minus cos 2a cos a plus sine 2a sine a. All right. So now before we can continue, we have to take out a negative. So I take out a negative and I'm left with cos 2a cos a minus sine 2a sine a. And then I can simplify this. So we have the negative in front. This inside here is cos, whereas this is my first angle, which is 2a. And then cos changes the sign, so this becomes plus, and then this is a. So this is just negative cos 3a. So that was simplifying. And now we're going to look at evaluating using special angles. Now, example 18, evaluate the following expression without the use of a calculator. Now here we have cos 40, cos 20, sine 40, sine 20. And none of these are special angles, and we're not allowed to use our calculator. So, but what we do see is we can identify that this is cos's compound angle identity. So before we get started, I can say, okay, this is cos. My first angle is 40, and cos changes the sign, so it must be plus and then 20 degrees. And this then simplifies to cos 60, which is a special angle. So to do that, remember your triangles. If you don't, then just go and revise special angles, where we have a 60-degree angle here and a 30-degree angle here. This is 1, 2, and 3. So with cos is adjacent over hypotenuse, so that would be 1 over 2. So cos 60 from the angle of 60, adjacent over hypotenuse, is 1 over 2. Question 18.1. Now we do the same here. In this case, we only have sine 280, cos 100, then cos 280, and sine 100. Now this is sine, then cos, then cos, then sine. So this one belongs to sine. And my first angle is 280. And then same sign. And then my second angle is 100 degrees. So now, to simplify this, this is just sine 180, and then the special angle to find the sine of 180, I'm going to draw the sine graph, which looks as follows, where this period after one period is 360, so half of that is 180. So I can see that sine at 180 is 0. So this value is equal to 0. Example 19. Once again, we're going to evaluate this without a calculator. And in this case, we've got sine 80, sine 40, sine 10, sine 50. So we don't see any corresponding angles that are equal. But what we can do is we can try and see, we can use this identity that says that sine theta is equal to cos 90 minus theta. So I can change a sine into a cos or a cos into a sine by simply saying the complementary angle. So these two angles needs to be the angle of sine and the angle of cos needs to be complementary. Then you can change them around. So let's change. I can see that this 40 and 50 are complementary, which means if I change, so let's say I change this one, and let's change these two. So actually no, let's change these two. So let's say this is then sine 90 minus 80, 90 minus 10, right? Because remember we need to, this needs to be still equal to this. So sine 80 or 80 is equal to 90 minus 10. Then the second angle is still sine 90 minus 50. All right, that's what 40 is equal to, 90 minus 50, minus sine 10 sine 50. Right, so now we use the reduction, and reduction says that if this is a 90, then this changes to cos. So cos, this would then be cos 10 times by sine, this changes then to cos, which is cos 50, minus sine 10 sine 50. Okay, so one of two ways, I've just done both. You can think about this as the complementary angles, or you can use reduction to change your sine into cos. So, and our aim with this was just to get the same angles, 10 and 10 and 50 and 50. All right, so now we can identify this as cos. So this is cos. My first angle is 10. Cos changes the sign to plus, and then second angle is 50. So 10 plus 50 is 60. So I've got cos of 60, and I draw my triangle. Right angle triangle. So this is the 60 angle, this is a 30 angle, 1, 2, and 3, and then cos is adjacent over hypotenuse, so this gives me 1 over 2, which is a half. Question 19.1, evaluate the following expression without the use of a calculator. So in this case we've got cos 20 times by cos 25 minus cos 250 times by cos 115. Now, I'm going to start with the most complex, well, not most complex actually, but the biggest numbers. And from the previous example, we kind of know what we're aiming for. We want to make, or we want to see if we can get these two angles to be equal, and also these two angles to be equal. Now, what I do know about 250 and 20 is that they add up to 270. So I can change this one. So I'm just going to rewrite this cos 20 degrees times by cos 25. And then minus, now this one I'm going to change into 270 minus 20. So this would then be applicable to the reduction formula, and where this 270 changes cos into sine. If you don't understand that, just go and recap the reduction formula. So here we have cos 270 minus 20. And then here, for the 115, if I can see what relationship is there between 25 and 115 degrees, I know that 115 is 90 plus 25. So in this case, I'm going to change the 150 into 90 plus 25 degrees. Alright, so now I'm going to apply the reduction formula to those two. So here we still have cos 20 degrees, cos 25 degrees minus, and then this, if we apply the reduction formula, we are working in for 270 minus 20, 270 is over here, and minus goes to tan's quadrant. So this means that this will then become negative sign, because cos is negative in this quadrant. So negative sine 20. And then for this cos 90 plus 25, so 90 is over here and plus goes this way. So that is sine's quadrant. So cos will then become a negative there, or is negative there. And then it changes into sine because of the 90. And then we have that 25 over there. Now we can just simplify this expression just by multiplying out the negatives. This negative and that negative just becomes a positive. So we still have that negative over there. So we have cos 20, cos 25 minus sine 20 and sine 25. Alright, so this then this represents our cos identity, our cos compound angle formula. So our angles are 20 and 25. Now we have cos, so the angles, which is 20, and then cos changes the sign to plus, and 25. So this then gives us cos of 45. Right, 45 is a special angle, so I can use my triangles to determine that without a calculator. If I have a 45 degree triangle, whereas this is 1, 1 and square root of 2, then cos says adjacent over hypotenuse, so that is equal to 1 over square root of 2. Now this is the answer, but now normally we don't leave our answer in where the surd is in the denominator. We have to rationalize the denominator. To do that, we can simply multiply top and bottom with square root of 2 over 2, and this will simply give us square root of 2 over 2. For example 20, evaluate the following expression without the use of a calculator. Now, in this case, if we have to not use a calculator, we normally want to aim for special angles. So if I have the 75, I'm going to try and break it up into special angles that I know. So we've got special angles as 0, 30, 45, 60, 90. Those are all special angles. So can I use one of these to get 75? I know that 30 plus 45 is equal to 75, so I can write 75. Instead of 75, I can write 30 plus 45. And then I can expand this with my sine identity, where I say that sine 30 cos 45, same sign, which is plus, and then cos 30 and sine 45. Alright, so since all of these are special angles, we can now just use our two triangles, the 30-60 degree triangle. This one is 30 and the 45 degrees. This is 1, 1 square root of 2. Alright, and this is 2, 1 square root of 3. So first of all, we need sine 30. So from the 30 degree angle, sine is opposite over hypotenuse, so that's a half. Then we have for cos 45 adjacent over hypotenuse, 1 over the square root of 2, plus cos 30 is adjacent over hypotenuse, so this is going to be square root of 3 over 2. And sine 45 is opposite over hypotenuse, so that's 1 over the square root of 2. All right, now at this stage, if you've substituted in these values, it would be safe to then use your calculator to just simplify it further. So I'm just going to type that in as a half times by 1 over the square root of 2 plus square root of 3 over 2 times by 1 over square root of 2. So my final answer then is the square root of 6 plus the square root of 2 over 4. Right, question 20.1. So we want to evaluate sine 15. So remember the special angles. They are 0, 30, 45, 60. Now, which ones can give us 15? So I can actually I can say 60 minus 45, that's equal to 15. Or I can use 45 minus 30. This will give me 15 as well. So let's use the first one, where I'm just going to replace 15 with 60 minus 45. Right, so now, once again, just to apply sine's compound angle identity, we have sine 60 cos 45 degrees minus cos 60 and sine 45 degrees. All right, now let's apply the angles, the special angles with our triangles. So 45, this is 1, 1 and square root of 2. And then with the 30, 60, so this is the 60, this is 2, 1, square root of 3. All right, so sine 60. 60 and sine is opposite over hypotenuse, so that's 3 over 2. Then cos 45, cos is adjacent over hypotenuse, so that's 1 over square root of 2. And then minus cos 60, 60 is adjacent over hypotenuse, so that's a half. And then sine 45, opposite over hypotenuse. And then we just type this into the calculator. So here we have square root of 3 over 2 minus okay, so then in this case we have square root of 6 minus square root of 2 over 4. Square root of 6 minus the square root of 2 over 4. Right, so that was evaluating using special angles. Let's look at doing calculations in quadrants using the cast diagram. Right, so for example 21, it says if sine p is negative 3 over 5, p is element of from 0 degrees to 270 degrees included, and cos q is 4 over 5, q is an element of from 180 degrees to 360 degrees included. Determine cos q minus p without the use of a calculator. Now, these are those questions where we have our quadrants, and the first thing we do is to find in which quadrant we need to work. So for this one, I'm going to use the angle of P, and this one is for my angle Q. Now, here we see that sine is negative. We know sine is negative in this quadrant and in this quadrant, the third and the fourth quadrants. And from 0 to 270, so we from 0 to 270, that's all three of these quadrants. Now, where both is applicable, where sign is negative, and where we inside this region, we will see that both are applicable in the third quadrant, and therefore we're going to draw our triangle in the third quadrant. So the angle P is this angle over here. Alright, now we're going to work out of this triangle as if we're working out of this angle alone. So that, and with that meaning that if I look at sine P being opposite over hypotenuse, my opposite is this. So this is my -3, and my hypotenuse is 5. Now on this side, okay, what we still need to do here is to find this length with Pythagoras. So to find the x, we have Pythagoras where we say x squared will be equal to 5 squared, the long side squared, so 5 squared, minus the other short side, minus -3 squared. So that means that x will be equal to the square root of 5 squared minus -3 squared. So let's just put that onto the calculator. We have the square root of 5 squared minus -3 squared. So this gives us 4. So this side then is 4 units long. Alright, now for our angle of Q, this is cos, and cos is positive in the fourth and the first quadrants, and our restriction is from 180 to 360. So that means from this 180 up to 360. So it either has to be quadrants 3 or 4. So both of these scenarios are applicable in the fourth quadrant. So I draw my triangle in the fourth quadrant, and that means angle Q is this angle, not theta, Q. Alright, so for sine, we're working out of this angle. For cos, it's adjacent over hypotenuse. Now the adjacent side is this one, which is 4, and hypotenuse is 5. And then we just need to use Pythagoras to find this side. So our y is equal to the square root of the long side, 5 squared, minus the short side, 4 squared. Alright, so this is then equal to (5 squared minus 4 squared), which is equal to 3. Now, you have to be careful with your signs. Here we have actually -3 because we are in the negative y values. If the triangle was on top here, this would be +3. Like we have this one actually also. This sign is -4 because here we're in the negative x coordinates. But the hypotenuse side is always positive because that's a length, and length in reality can't be negative. Alright, so now we can get started. We need to find cos Q minus P. So since we are on compound angles, or even if we're not, if you find this question just randomly in an exam, you can immediately see we have two angles in our cos identity or cos formula. So immediately think in compound angle direction, and then we write out our compound angle identity. So it's cos Q cos P, and change the sign, sin Q sin P. Alright, now since we have these on their own now, we can use our triangles to determine cos P, cos Q, and some of them we're already given. Like for example, we're given sin P already and cos Q. So cos Q we're given as 4/5, and then cos P, from the P angle, we know that cos is adjacent over hypotenuse, so adjacent is this side over here, so it's -4/5, plus, so sine P, okay, sine P is that one, but let's just find sine Q. So sine Q is opposite over hypotenuse. So opposite minus 3 over 5. Now for sine P, sine once again opposite over hypotenuse, and P over here, opposite is negative 3 over hypotenuse, which is 5. So negative 3 over 5. Now this I can quickly simplify without a calculator. I've got 4 times by a negative 4, that's negative 16 over 25, plus negative 3 times negative 3 is 9 over 25. So negative 16 plus 9, or the difference between 16 and 9, that's 7, so it's negative 7 over 25. So for question 21, over here we've got cos A is 4 over 5, sin A is negative or less than 0, and then cos B is 12 over 13. We've got this restriction over here, and we need to determine sine A minus B. Alright, so first of all I'm going to draw my quadrants, one for the angle of sine and one for the angle of B. So for cos A to be positive, cos is positive in these two quadrants, and where is sine negative? Sine is negative in these two quadrants, therefore my triangle will be drawn in the fourth quadrant. Now cos is adjacent over hypotenuse, so adjacent is 4 over hypotenuse is 5, and we can use Pythagoras to determine this side, and we've done it in the previous example and we saw that it's negative 3. Alright, and then to find the angle of cos B, now this one is positive over here, so it's going to be either these two quadrants. Our restriction says 0 to 90, so it's going to be the first quadrant, just from 0 to 90. Alright, now cos is adjacent over hypotenuse, so adjacent, if this is my angle B, adjacent is 12 over 13. So let's use Pythagoras to find this side over here. We want the y, so y squared, or let's do it down here, y squared is equal to my long side minus my other short side. So that's going to be 13 squared minus 12 squared. Alright, so y is equal to the square root of 13 squared minus 12 squared. And then I'll just put that on the calculator. So we have the square root of 13 squared minus 12 squared, and that gives us 5. So this is 5, and all of these are positive because this is in the positive y coordinates and this is in the positive x coordinates. Now I can go ahead, I'm going to expand this, so this is sine A cos B, same sign is minus, and then cos A sine B. Alright, sine A, to find sine A, we go to A's angle, and we're working out of this angle, and we know sine is opposite over hypotenuse, so sine A will be negative 3 over 5, and then cos B, we are given cos B, that's just 12 over 13, minus, so cos A is also given to us, that's 4 over 5, and then finally sine B, from sine it's opposite over hypotenuse, so it is 5 over 13. Okay, so let's put this into the calculator. So we have a negative 3 over 5 times by 12 over 13 minus 4 over 5 times by 5 over 13. Right, so that gives me negative 56 over 65. Alright, so that was using the cast diagram. Let's look at some identities. So example 22 says prove the following identity. And if you remember with identities, we always want to start with the complex one. Let's go back. Complex one first. So this would be this side, the left-hand side. So also remember we have to start by saying left-hand side is equal to, and then copy the whole thing just as our statement. This is what it's equal to. Alright, now I'm going to use the compound angle formula just to replace these two with their identity. So cos is cos B, cos Q, and then opposite sign is minus sine B, sine Q. On this side, we have cos B, cos Q. Opposite sign is plus sine B, sine Q. Alright, now let's look at some terms that are the same. We have cos B, cos Q here and here, and they are added together, so this will be 2 cos B, cos Q, and then minus sine B, sine Q plus sine B, sine Q, that equals to 0. So this is then our final answer, which equals to the right hand side. So then we've proven our identity. So prove the following identity, and once again we're going to start with the left hand side. So left hand side is equal to sine A plus 30 and minus sine A minus 30 degrees. Okay, so expanding that, we get sine A cos 30 plus cos A sine 30 minus, now because of this negative over here, I'm going to just put this whole one's formula into brackets. This will then be sine A cos 30 minus cos A sine 30. Right. Multiply out the brackets. So this we just copy over. Minus sine A cos 30 plus, if we multiply in the brackets to both terms, plus cos A sine 30. Alright, now our terms that are like terms, we've got a sine A cos 30 over here and a sine A cos 30 over here. The one is plus, the other one's minus, so they equal to 0. And then we have cos A sine 30, cos A sine 30, both are added together. So if we add, for example, x plus x, we get 2x. So if I add these two together, I just get 2 cos A sine 30. Now, this sine 30 is a special angle. I'm going to draw my triangle here, my 60, 30 degree triangle. So my 30 degrees are there, 1, 2, and square root of 3. So for sine, it's opposite over hypotenuse. So this is 1 over 2. So this is 2 cos A, and I replace sine 30 with 1 over 2. Now this 1 over 2 and this 2 over 1, they cancel each other, which means we are only left with cos A. And that is our right-hand side. So we say that's equal to the right-hand side, and then we've proven our identity. For example 23, we need to prove the following identity. So over here we can once again start this side, and the first thing I'm going to do is, now this one looks more complicated, but the reason I'm using this one is I can actually instead of 2 theta, I'm going to write it as, okay, let's start in the right way. Say that we're going to start on the left hand side, which is equal to cos 2 theta, and I'm going to change this 2 theta into cos theta plus theta, and then I'm just going to expand it using my compound angle identities formula. Cos theta minus sine theta sine theta. Okay, simplifying that, we get cos squared theta minus sine squared theta. Now let's just have a peek at what we're aiming for. We want this. Now we already have a cos squared over there. So what I know from this identity, we can actually start now from this side. Let's do that. Because we know this identity where sine squared theta plus cos squared theta is equal to 1. So I'm going to replace this 1 with this identity. So if we now start from the right hand side and we say 2 cos squared theta minus 1, where we say the 1 is equal to this, we have minus, and in brackets because there's a negative in front, sine squared theta plus cos squared theta equals to 2 cos squared theta, so minus sine squared theta minus cos squared theta. Alright, and then we can see that we've got these two like terms, 2 cos squared theta minus cos squared theta, so this just gives me cos squared theta, and then we have this term minus sine squared theta. So here we have left hand side equal to right hand side. Now all of this went quite smoothly as I did it, but normally first approach, even for me, it doesn't always go as smooth. Well, more practice makes it go more smooth, of course, but with these types of sums, they are difficult, and sometimes even for me I have to like substitute in, try different things, play around with it, substitute in different identities, see, okay, that didn't work, then try again with something else. So if this seems hard, that's normal, but definitely more practice on this makes it really easy. Right, question 23.1, we have the following to prove. So I'm just going to go ahead and do the same procedure as I did with the previous one, where we just broke up this, or we just wrote this as p plus b. So we have, we're starting with the left hand side, and that's equal to sine 2p, and I break that up as sine p plus b, and then I expand it, so I have sine p cos p plus cos p and sine p. Alright, so this says sine and then cos, then sine, but this is in actual fact xy is equal to yx. So these are in actual fact like terms. I can just swap these two around. So I have sine p cos p plus sine p cos p, and then if I add my two like terms, I get 2 sine p cos p, which is equal to the right hand side, of course. Example 24. So we need to prove the following identity. Alright, so if we just hold on for a minute and we look at this, over here we've got 5a, 3a, and then out of the blue we have this 2, 4a cos a. Now, and still keep in mind what we did with the previous examples where we broke these angles, or we broke our angle up. Now, if we want to, here we'll have to look at our result to determine what are we going to start with, because here we want to end up, we're starting with a 5 here and a 3, and we end up with a 4 and a 1 a. So if I want to go there, what I'm going to try and do is, if I break this up, remember I can break it up into anything, 1 plus 4, 2 plus 3, whatever. I'm going to break it up into what was given at the end. So here, I'm going to replace this one with these numbers. So I can make 5 with 4. I can say 4a plus a. And then over here, I can also use 4 and 1 to get 3. I can say 4a minus a would give me 3. So if I start, I say left hand side is equal to sine 5a plus sine 3a, right? Then we just break them up as sine 4a plus a plus sine 4a minus a. Okay, so now let's expand. So this is sine, so we have sine 4a cos a plus cos 4a sine a plus, now expanding this side, we have sine 4a cos a minus cos 4a sine a. Alright, so we're getting closer. We already have, we can see we've got something with this identity in. So for the sine first, sine 4a, we have this and this, and that's like term. So if we add that, we get 2 sine 4a cos a, and here we have cos 4a, and there cos 4a sine a. The one's plus, the other one's negative, so that means they add up to 0, and this then gives us our right hand side. Question 24.1. So as the previous example, let's look if we can do the same. We want 3 and 2. For 5, we can say we break that up into 3a plus 2a. And over here, for 1a, we can say we break that up into 3a minus 2a. Okay, so our left-hand side is equal to cos 5a plus cos a. And then breaking them up, we have cos 3a plus 2a plus cos 3a minus 2a. Okay, let's expand. So we have cos 3a cos 2a, change the sign, minus sine 3a sine 2a plus cos 3a cos 2a, change the sign, becomes, I'm just going to rewrite this here, or right here at the bottom, change the sign, plus sine 3a cos 2a. Okay, let's look out for our like terms. Starting with the cos 3a, we have this one, and they add up, and they add up to 2 cos 3a cos 2a. Here we have minus sine 3a sine 2a plus sine 3a. So, this must be a sine. Alright, they add up to 0, and then once again we have the right hand side. So for example 25, prove the following identity. Now as you can see here, if you already done reduction formula, which you should have, this is simply the reduction formula for sine 180 plus theta, but we are going to try and use, we need to prove this reduction formula is valid. So since we have two angles inside here, we can expand it with compound angles and see if we get to this. So we start with the left hand side, and we have sine 180 plus theta, and then we expand it. We have sine 180 cos theta plus cos 180 and sine theta. Okay, this 180 degrees are form part of our special angles, or the angles that we can find without a calculator, and in this case we use the graphs. We know our sine graph looks like this, where it goes up to 360 and where this is 180. So it's easy to see that sine 180 is equal to 0, right? So this will then be 0. So I'll just write down my cos theta here. Then for cos 180, if I draw cos's graph, it looks like this, where this goes up to 1, this is down to minus 1, and here we have 360 degrees. Half 360 degrees is over here, which is 180. So cos on 180 is equal to -1. So here we have -1 sine theta. Alright, so 0 times by anything is 0. And then -1 times by sine theta. So this gives me minus sine theta, which is equal to the right-hand side. Right, so prove the following identity. Here we have sine 270 plus theta equals to negative cos. Our left-hand side is equal to sine 270 plus theta. Expanding that, we get sine 270 degrees cos theta plus cos 270 degrees sine theta. Okay, once again, 270 is one of the angles we can read off the graphs. So my sine graph, where this is 360, 180, 90, and 270 over here. So, and then let's just draw the cos graph while we at it, which looks like this, and our 4 points, 90, 180, 270, and 360. Right, so for sine 270, it's equal to -1 plus, and cos 270 is on 0. So simplifying this expression, we have negative cos theta. This becomes 0, which is then equal to the right-hand side. So that's it for identities. Let's look at equations. Right, so for example 26, find the general solution of the following equation. Now, once again, it would help to know your compound identities off by heart, because then you'd immediately recognize something familiar. We've got exactly the same angles, whereas we have got sine, cos, cos, sine. So this is equal to the sine formula, where I can rewrite this as sine. My angles are theta. It stays the same sine with sine, so minus 40 equals to 0,5. All right, now at this point, hopefully you are confident with your equations, your trigonometric equations. At this point, we can use the QRS method. So quadrants are first. Where is sine positive? Sine is positive in the first quadrant and in the second quadrant. My reference angle, so for that I use my calculator. I say shift sine and type in 0.5, and that would give me my reference angle as 30 degrees, and then I solve. So we start with the first quadrant, and the first quadrant is just my reference angle plus 360k. So theta minus 40 degrees is equal to my reference angle plus 360k, because sine repeats itself every 360 degrees. And then just to finally solve for theta, theta is equal to 30 plus 40 degrees plus 360k, and this is equal to 70 degrees plus 360k. Or our solution in our second quadrant. So for the second quadrant, we have we start with theta minus 40, which is equal to, now second quadrant is 180 minus my reference angle, so 180 degrees minus 30 degrees plus 360k. And then solving for theta, we have 180 minus 30 plus 40 plus 360k is equal to, this is just minus 30 plus 40, that's 10, so this is 190 degrees plus 360k. Question 26.1. Now we have sine theta, sine 35, cos theta, cos 35. This resembles cos's compound identity. If we swap these two around, because this is a plus, it would just resemble the same cos theta, cos 35. So this then I can rewrite as as cos theta plus, cos changes the sign, so minus 35 degrees, and that's equal to sine 50. Alright, now don't get thrown off by this sine over here. Sine is just a number. So if I type sine 50 into the calculator, and it's important to do that before you get started with the QRS method, because this is possible to be negative. But in this case, it's just a positive number. And so to start off with QRS, we're going to ask, where is cos positive? We know cos is positive in the first quadrant and in the fourth quadrant. And our reference angle is then just the shift or the inverse of cos of that number. So if I say shift cos of sine 50. Oops, I think I put one too many brackets. Yes, that's 40. 40 degrees is our reference angle, and now finally to solve for the first quadrant, it's just the reference angle. So theta minus 35 is equal to my reference angle 40 degrees plus 360k. So theta is equal to 40 degrees plus 35, if I bring the 35 over, plus 360k. And then theta is equal to 75 plus 360k. Alright, to solve for the fourth quadrant is 360 minus my reference angle, so theta minus 35 is equal to 360 minus 40 degrees plus 360k. So theta is equal to 360 minus 40 plus 35 plus 360k. Alright, so minus 40 plus 35, that gives me negative 5. So 360 minus 5 is 355 plus 360k. So that's my general solution for this equation. Okay, that means we are done with equations as well.